Welcome to the Astrum Crew Resource Management Training course. At the end of this first lesson you will be able to outline the origins of CRM, describe the system concept as it applies to aviation, describe some essential properties and components of a system and, finally, explore how the system behaves. Commercial aviation is like a puzzle with many parts. They all need to fit together if it is to work. This lesson explores aviation as a system. Since the very first formal pilot training course, developed in 1917, flight instruction has concentrated on the control of the aircraft. On the 27th of March 1977, two Boeing 747 passenger aircraft collided on the runway at Tenerife, in the Canary Islands. 583 passengers and crew died, making this the worst aircraft accident in history. The investigation found that interactions between crew members was a possible causal factor. The following year, on the 28th of December 1978, a United Airlines DC-8 crashed on the approach into Portland, Oregon, leaving 10 dead. Again, crew performance was a factor. It is easy to think that, because modern aircraft are so reliable, accidents are now caused by humans. A study of collisions between ships around the United Kingdom, published in 1882, found that 60% were the result of what the authors called human error. A study published in 1933 looked at 355 aircraft accidents in the United Kingdom. Just over a quarter were solely because of technical failure. A half were failures of airmanship. A review of 100 Australian aircraft accidents between 1921 and 1932 found a similar result. The human has always been the largest contributor to safety problems. We were looking at the very fragile technology when we should have been looking at the very fallible human. A 1979 NASA conference is now seen as the moment when aviation recognized that safety was built on more than just an ability to fly the aircraft. It was at this conference that CRM was first defined, the use of all available resources, information, equipment, and people to achieve safe and efficient flight operations. Crew resource management is a part of the broader field of human factors. It includes aviation medicine, for example, the effects of flight at altitude on the human body. It also includes ergonomics, which is the design of workspaces and interfaces, and, finally, social psychology. CRM is about what happens when these three areas. But CRM is not static and has developed over the years. In the 1990s, threat and error management, or TEM, was developed as a structure to describe normal operations. More recently, the safety eye concept argues that accidents and serious incidents are very rare. So, rather than focus on what goes wrong, we should concentrate on how people get things right every day. To understand why things go right, we need to take a systems view of aviation. A system is an arrangement of human and technical resources brought together to achieve an operational goal. Different parts of the system will have different goals, but all systems aim to deliver outcomes that are predictable and consistent. The performance of the system should be reliable and, of course, safe. There are two important properties of all systems. First, non-ergodicity, which simply means nothing ever happens the same way twice. Even if the differences are only minor, we still have to adapt to keep control of things. Non-ergodicity and the need for flexibility is an important aspect of human behavior. The second property is radical uncertainty. Things will often fail in ways we cannot anticipate. Procedures, checklists and training cover most of the job, but crews still need to cope with changes and surprises. That is why we need CRM. A system is made up of components, each of which has a specific function. The first element in our aviation system is the pilot. You make inputs to the aircraft and monitor the results through control forces, displays and the way the world around you changes. Because aviation is complex, activity is shared between different agencies. The team may be very real, as in the crew on the aircraft. But the team can also be a virtual one that forms and reforms as the flight unfolds. On the ground, the baggage handlers, refuel and ground ATC all form part of our team, but once we get airborne, now the departures controller joins our virtual team and the other agencies go and join new teams. Airlines and aircraft manufacturers are a part of the system. Airlines make decisions about what routes to fly, what aircraft types to use, what procedures to follow. Manufacturers design and build aircraft. The decisions they make shape the way pilots do their job. Regulators organize the infrastructure that supports aviation. Airports, air traffic services, weather information providers and so on. They also develop the rules that guide the conduct of aviation. They exercise oversight. Each level in the system exercises control over the level below. This may be through regulations, procedures, instructions, or by granting permission for activity. Performance is monitored by feedback loops. These may be simple acknowledgements or formal reports. Emergence describes system behaviors that cannot be predicted simply by how the component parts work. At the regulatory level, trust in the safety of aviation is an emergent property. In organizations, morale is an emergent property. Efficiency flows from how teams interact. Most important, safety is an emergent property of how you do your job. In a system, all activity occurs within a bounded space. A boundary represents the point at which the system transitions between states. Safe to unsafe, for example, or legal to illegal. The concept describes the volume of space and time available to accomplish the task. For example, on final approach, the boundary is the point by which the pilots must have reduced the energy state of the aircraft sufficiently to allow a safe landing. Buffering describes the number of different ways to get the job done and still stay within the boundary. We can see this in the relationship between procedures and techniques. The procedure is the goal and the different techniques are ways to achieve that goal. For example, an airline will have a procedure for flying an approach. But if the pilot has too much speed, he can get rid of any surplus energy by using speed brakes or by lowering the undercarriage earlier than normal. Techniques represent the system's buffering capacity. Tolerance describes the nature of system failure. On the one hand, we have graceful degradation as we manage to retain some control, while on the other we see catastrophic failure. If we look at landing again, a failure to reduce the energy state of the aircraft might result in a firm landing. A graceful degradation, maybe, but could also result in escalating harm from damage to the aircraft or a catastrophic runway excursion. A system may have multiple boundaries. If we shed energy too early or too quickly, then we run the risk of stalling the aircraft. This would be a catastrophic excursion. Form the aircraft's flight envelope, a set of boundaries. The inquiry into the loss of the 1986 Challenger space shuttle explosion uncovered another aspect of systems behavior: safety drift. Over time, what is thought to be normal behavior starts to creep towards the safety boundary. The problem is that this change goes unnoticed until something goes wrong. On the 31st of January 2000, an MD-83 aircraft crashed into the sea off the coast of California when the screw jack that moved the tailplane failed. A failure to properly lubricate the screw jack resulted in excessive wear and, ultimately, failure. All 88 passengers and crew on board died. Safety drift can take many years to become visible. The MD-83 screwjack was supposed to be checked and lubricated every 300 to 350 hours. Over the years, periodic rationalization of maintenance schedules meant that lubrication was happening about every 2,000 hours. The system boundary here was the point at which the screwjack system lost integrity. On the 17th of January 2004, 10 people died when a Cessna Caravan crashed after takeoff from Pelee Island in Lake Ontario. Because Lake Ontario freezes in winter, the Government of Ontario arranges for charter flights to keep a communication link with the small community on the island over the winter. On the day in question, the pilot tried to take off in icing conditions in an overweight aircraft. Lake Ontario freezing up is a system environment factor. The Government of Ontario and the airline operating the charter are organizational actors. Transport Canada was the regulator. The flight operations inspector responsible for overseeing the airline was not told of this new task. The airport at Pelee Island has no de-icing facilities and, so, as part of the planning for the route, the airline provided spray cans of de-icing fluid to be carried on the aircraft. The pilot on the day did not take the sprays even though icing was forecast. On the flight to Pelee Island, the aircraft was already becoming covered in ice. People on the ground spoke to the pilot about the ice, but he still decided to take off for the 15-minute return trip. The Pelee Island crash illustrates all of the topics discussed in this lesson. In this lesson you have reviewed the development of CRM, defined the system concept as it applies to aviation, looked at the essential properties and components of a system and seen how a system behaves.